Please label these notes integrals to notes, trapezoid, and midpoint Riemann sums and write today's date. By the end of this lesson, you should be able to use trapezoidal and midpoint sums to approximate the area under a curve, or approximate an integral. So in integrals 1, we looked at left and right Riemann sums, and we noticed that especially when we only use a few subintervals, the left and the right sums overestimate or underestimate by a substantial amount. The trapezoidal sum and midpoint sum give us much more precise estimates. So that's what we're working with today. So let's start off with the trapezoid and midpoint. And we'll just compare the two. So with the trapezoidal sum, you'll see something looks like this. So estimate the integral from 0 to 4 of x squared dx using two subintervals and a trapezoidal Riemann sum. Trapezoidal is by far the most commonly used one, but midpoint we'll also see something like this. Estimate the integral from 0 to 4 of x squared dx using two subintervals and a midpoint Riemann sum. So our first step, as before, was to sketch it. And let's leave a little bit of room down here. So x squared is just that parabola shape. And we're going from 0 to 4, 1, 2, 3, 4. Same thing over here. Okay? And there are a couple of key things that we have to remember in order to do these problems. One, the area of a trapezoid in this case is going to be height 1 plus height 2 over 2 times the base. This is also expressed as base 1 plus base 2 over 2 times the height, but for us the height is going up and down here, and basically what we're going to do is we're just going to do the average of the two heights and then multiply by the base. Over here, the thing to remember, the midpoint is in the middle of the interval. Actually, I just want to write this in over here so I make sure that we have it. That what this really means is the average of the two heights. So rather than just lining us up with one, or like the left side or the right side, in this case we're actually going to use both. So we're going from 0 to 4, so we're starting here at 0, we're ending here at 4. And it says two subintervals, 1, 2, 3, 4. We'll divide that in half. It's right here. And what we're going to do is we're going to draw our heights up to both of the left and the right hand side of the interval. And then to make the trapezoid, we're just going to connect them. And same thing over here, we're going to draw this up to, I have to extend it a little bit more, up to there, and then draw that to connect it. So what I'm going to do is I'm going to find each of these heights. So this height right here, when x equals 0, x squared equals 0. For this height here, 2 squared equals 4. For this height here, 4 squared equals 16. So So when I'm estimating this, remember the little squiggles mean approximately equal to. What I'm going to do is I'm going to take the average height here, so 0 plus 4 divided by 2. I'm going to multiply that by the width, which we can see is just 2. And then for this one I'm going to take the average height, or 4 plus 16, over 2. And then multiply by the width, which again is 2. So this is going to give me 4 divided by 2 is 2, times 2, plus 4 plus 16 is 20, divided by 2 is 10, times 2. And when I multiply that out, 4 plus 20, 24. With a midpoint, I'm starting at 0, I'm ending at 4. And if I divide it into two pieces, it's right there. The midpoint means that the height of the rectangle is just equal to the y value, or the f of x value, of the x value that's in the middle of the interval. So between 0 and 2, the middle is 1. So that's how high the height is going to be. Between 2 and 4, the middle x value is 3. So that's how high it's going to be. And the reason that we use these is that now we have a little bit of an overestimate, a little bit of an underestimate, a little bit of an overestimate, a little bit of an underestimate. And the goal is sort of that these sort of fill each other in until we have something that's pretty close to the actual number. Same here. These are much, much smaller overestimates than we typically would have for the left to right Riemann sums. And so this is a much more accurate estimate. So here what we're going to find is if I'm finding the height of this one, I'm going to use this 1 to find the height, because that's right in the middle. So 1 squared equals 1. Over here, this height, 3 squared, equals, 9. And then there's widths of 2 again. So over here, we're estimating the integral from 0 to 4 of x squared dx approximately equals this height, which is 1, times the width, which is 2, plus this height, which is 9, times the width, which is 2. When we multiply those and add them up, we get about 20. So that's the basic idea of those. There are a couple of characteristics to know. In terms of overestimating versus underestimating, for trapezoidal sums, again, it overestimates versus underestimates in different conditions. But instead of being overestimating or underestimating based on whether the function is increasing or decreasing, the trapezoidal sum behaves differently based on whether the function is concave up or concave down. So for example, if it's concave up, and we're going to draw our little trapezoids, whether it's increasing or whether it's decreasing, when we connect to these points, this is going to overestimate. Here's our little curve here. If it's concave down, then when we draw our little trapezoids, whether the function is increasing or decreasing, the trapezoidal sum will underestimate. For the midpoint sum, underestimating and overestimating is actually a very difficult thing to figure out. It's not covered on the AP Calc exam. Let's do a couple check for understanding problems with this. First, let's estimate the integral from -1 to 5 of x cubed plus 2 dx using midpoint Riemann sums with width 2. So the first thing is it's helpful to have some sense of what this looks like. Here are axes. Here's the function. It looks something like that. We don't have to be real precise with this sketch, but we do know that x cubed kind of looks like this, and we do know that plus 2 moves it up, so that means it's going to look something approximately like this. So we've got negative 1, 1, 2, 3, 4, 5. And we know that we're doing with sums of width 2, so that means we're going from negative 1 to 1, from 1 to 3, and from 3 to 5. If we're doing a midpoint sum, that means we go up the midpoint. So that means that to estimate the integral from negative 1 to 5 of x cubed plus 2 dx, that's going to approximately equal, let's see, the width here is 2. Then this height is going to be f of 0. Let's call this f of x. Where we're getting that from again, this width is 2. Then the same thing for this one. The width is 2, the height is whatever f of 2 is. This one, the width is 2, the height is whatever f of 4 is. Now you can work these out on the side if you like, or you can work them out here. But we do know that f of x is this x cubed plus 2. So that means we've got 2, 0 cubed plus 2 times 2 cubed plus 2 times 4 cubed plus 2. This is approximately equal to 2. 2 times 2 is 4. This is approximately equal to, this actually equals 10. 10 times 2 is 20. And this equals 30. This equals 66, so 2 times 66 is 132. And there's our answer. Let's do a second one with trapezoidal sums. So we'll estimate using trapezoidal sums with width 3. Same diagram as we had before. Looks something like that. Go ahead, try this one on your own. Restart the video when you're ready. Okay, so we're doing trapezoids of width 3. So we're starting there. 1, 2, 3 takes us there. 1, 2, 3 takes us there. So that means we're going up and then connecting, going up, and then connecting. And we can see that this width here is 3, this width here is 3, and when we're using these heights here, f of -1 is going to be -1 cubed plus 2, or 1. F of 2 is going to be 2 cubed plus 2. F of 2 is 10. And f of 5 is going to be 5 cubed plus 2, or 127. Now when we come over here to do our estimate, we're estimating the integral from -1 to 5 of x cubed plus 2 dx. So for our first trapezoid, the height or width, depending on whatever one you call it, that's 3. Then we're going to multiply by the average of the two different heights or bases, whichever one you want to think of it as, but the average of the two red lines. So 1 plus 10 over 2. And then same thing for the second trapezoid. This width down here is 3. Height 1 is 10. Height 2 is 127. Divide by 2. When we do all that, we end up with 16.5 plus 205.5, or approximately 222. The final thing you should be able to do is work with data in a table. Using the subintervals indicated in the table below, estimate the integral from 3 to 8 of f of x dx using trapezoidal sums. Now notice, this is from 3 to 8. That means start at 8, end at 3, even if there are more values in the table. So here's our table. Here's x, f of x, 1, 3, 5, 8, 10, 2, 1, 4, 6, and 12. Notice the widths do not have to be the same. I find it helpful to just make a quick sketch of this to make sure that I keep all my widths at the proper amount. So we're going from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice we are going to be starting at 3 and stopping at 8. So that's all that we really care about. At 3, the height is 1. At 5, the height is 4. And at 8, the height is 6. I don't really even need the y-axis over here. I just need to have a sense of how high they are relative to each other. So let's go ahead and make some trapezoids. Notice that this one here has a width of 2. This one here has a width of 3. They do not have to match if we're given data from the table. So for this trapezoid, the width is 2. Then we'll find the average of the two heights. Notice it's just these heights right here. Basically all we're doing to find this width is subtracting the x values, and then we're just using the two f of x values right here. Here the width is 3, that's 8 minus 5. And then the average height is 4 plus 6 divided by 2. When we simplify all that out, that's 5 plus 15, or approximately 20. This concludes these notes.